Hello, I'm Matthew Colless and I'll be talking about recent results and future plans for peculiar velocity surveys, focusing on their use as a probe for cosmology. Peculiar velocities are the motions of galaxies that are distinct from the overall expansion of the universe and result from the inhomogeneous mass distribution. In the linear regime, a galaxy's peculiar velocity is proportional to the acceleration it experiences due to the gravity of the encompassing matter and the overall growth rate of structure in the universe. Peculiar velocities in the linear regime can therefore be predicted, up to a constant factor, from the galaxy distribution observed in redshift surveys. So measuring peculiar velocities tells us about the product of the growth factor and the amplitude of matter fluctuations. Thus, redshift surveys and peculiar velocity surveys are highly complementary. But whereas redshifts are observationally easy and cheap, peculiar velocities require redshift-independent distances and so are observationally hard and expensive. Nonetheless, the additional information they can provide makes them an increasingly valuable adjunct to the massive redshift surveys now underway or planned. The value of peculiar velocities is that they provide information not available from redshift surveys. For example, we can measure the typical bulk flow, the mean peculiar velocity, as a function of scale for spheres of varying sizes to see if this matches the predictions of the standard cosmological model in terms of amplitude, shape, and convergence to zero bulk motion on large scales. We can also measure the growth rate of structure, f sigma 8, at low redshifts, where any potential deviations from the standard cosmological model would be largest, and where redshift-based distortions cannot be used. And of course we can also measure the velocity power spectrum and the galaxy velocity cross-power spectrum to obtain additional constraints on cosmological models. In this talk I'll present some results from recent analyses of existing peculiar velocity surveys before going on to discuss the prospects from upcoming surveys. First, I'll talk about the results from a joint analysis of the 60FGS and SDSS peculiar velocity surveys and an extended SDSS peculiar velocity catalogue. The 60FGS survey provides peculiar velocities based on fundamental plane distance estimates for about 7,000 galaxies over 17,000 square degrees of the southern hemisphere. Our analysis of the SDSS survey data provides additional fundamental plane distances and velocities for nearly 9,000 galaxies over about 10,000 square degrees of the northern hemisphere. Combining these gives a sample of about 16,000 galaxies covering 3/4 of the sky. Over the volume out to a redshift of about 15,000 kilometers per second, the residual, that is to say unaccounted for, bulk motion of galaxies points in a direction very close to that predicted from the redshift space distribution of galaxies in that same volume. However, the amplitude is larger than predicted, presumably due to structures at higher redshifts such as the Shapley and Vela superclusters, which lie at or beyond the limit of the survey volume. We therefore fit these 16,000 measured peculiar velocities to a model derived from the galaxy redshift distribution plus a residual dipole approximating the effect of more distant structures. This model fit gives an estimate of the growth rate of structure at a redshift of about 0.05. Combining this measurement with other estimates of f sigma 8 from both peculiar velocity surveys and redshift space distortions gives joint constraints on sigma 8 and omega matter. The 60FGS plus SDSS measurement is consistent with most other measurements in preferring an estimate of sigma 8 that is lower than that expected from Planck. In fact, the joint omega matter and sigma 8 constraints prefer one or more of the following things: a matter fluctuation amplitude sigma 8 that is less than 0.8, a Hubble constant that is greater than 70 kilometers per second per megaparsec, and or a growth index greater than the 0.55 expected from general relativity. These results are consistent with other indicators of tension between high redshift, that is to say CMB, and low redshift measures of H0 and sigma 8. Subsequently, we have extended the SDSS peculiar velocity sample limit from 15,000 km per second to 30,000 km per second. Together with an improved 60 FGS sample of about 9,000 galaxies and the Cosmic Flows 4 Tully-Fisher sample of about 10,000 galaxies, we now have more than 50,000 peculiar velocities over the whole sky. This is a significant improvement in sample size and coverage. There are two caveats to this, however. First, the sample is still missing galaxies in the zone of avoidance close to the plane of the galaxy. And second, because the peculiar velocity errors are proportional to distance, the 25,000 galaxies in the Sloan sample at distances greater than 15,000 kilometers per second are much less constraining than the nearer 25,000 galaxies. With those caveats, however, the extended SDSS sample gives us the best measured estimate of the bulk flow on large scales to date. Depending on the details of the fit, we find the bulk flow within a sphere of effective radius 150 on H megaparsecs has an amplitude of between 320 and 380 kilometers per second, with an uncertainty of about 100 kilometers per second. This is about 2 sigma greater than expected for the RMS bulk motion on this scale in the standard lambda CDM model. This excess bulk motion might be due to large nearby mass concentrations, such as the Shapley and Vela superclusters. However, it should be noted that the partial hemisphere covered by SDSS means there's significant uncertainty in one component of this bulk motion. Complementary to these new peculiar velocities based on fundamental plane distances for early type galaxies, we've also reanalyzed the peculiar velocities derived from Tully-Fisher distances for the late type galaxies in the Cosmic Flows 4 data compilation. This reanalysis of the alfalfa H1 data in Cosmic Flows 4 uses a new one-step method for estimating Tully-Fisher distances, whereas the traditional method first calibrates the Tully-Fisher relation on galaxies and clusters and then derives distances for the rest of the sample from this calibrated relation. We simultaneously fit the Tully-Fisher relation and the distances using a velocity field model derived from redshift surveys. We apply this new method to the subsets of the Cosmic Flows 4 data with alfalfa H1 line widths and photometry either from SDSS, a denser sample in the northern sky, or from WISE, a sparser sample but covering the whole sky. We get reasonably consistent results from these two partially overlapping samples, as shown in the table and the corner plots. The purple results are coming from SDSS plus H1, and the orange results from the WISE plus H1 sample. As with our analysis of the 60 FGS plus SDSS sample, we find excellent agreement between the direction of the observed bulk flow and that predicted from galaxy redshift surveys. But again, the amplitude of this bulk flow is larger than predicted, with a residual bulk motion of about 300 kilometers per second. The constraints on the growth rate from these Cosmic Flows 4 samples are also consistent with those from 60 FGS plus SDSS, and prefer a lower value of F sigma 8 and a higher value of the growth index at low redshift than predicted by the Planck parameters for the standard cosmology. These recent analyses of the best existing peculiar velocity surveys thus provide some intriguing hints that there's more to be discovered if only we had larger samples of more precisely measured peculiar velocities. Two surveys that will take big steps in this direction are the Wallaby H1 survey with the Australian SKA Pathfinder and the Foremost Hemisphere survey, 4HS, with the Foremost instrument on the upgraded Vista telescope. Wallaby will measure peculiar velocities using H1 Tully-Fisher distance estimates for about 50,000 galaxies, These are the galaxies with suitable inclinations and signal to noise in the survey, and are expected to represent about 10% of the 500,000 galaxies expected to be detected by this blind H1 galaxy survey of the Southern Hemisphere. The Wallaby peculiar velocity sample will be more than 10 times larger than the existing cosmic flows sample and will yield proportionately tighter constraints. This is demonstrated in the comparison of the corner plots, which shows the joint constraints on the velocity model parameters. Purple and orange in these plots are, respectively, the optical and infrared samples from Cosmic Flows 4, while blue and green show the equivalent samples from Wallaby. The Foremost Hemisphere survey will use the fundamental plane to measure about 500,000 distances for early type galaxies out to a redshift of 0.12. 4HS will cover about 20,000 square degrees of the sky, pushing close to the galactic plane and into the northern hemisphere. The survey is expected to begin in 2025 and should measure about 100,000 peculiar velocities each year for the following 5 years. The Wallaby and 4HS surveys of the southern sky will be complementary to the ongoing DESI peculiar velocity survey in the north. Together they will measure, of order, 750,000 peculiar velocities over 3/4 of the sky. This order of magnitude increase in the number of peculiar velocities will lead to correspondingly more stringent constraints on cosmological parameters. For example, this figure shows the constraints expected from the 4HS peculiar velocity survey on the bulk flow as a function of scale. It indicates that the bulk flow will be measured on all scales up to about 300 megaparsecs to a precision corresponding to better than 20% in sigma 8. Similarly, these surveys will yield much stronger constraints on the growth rate of structure. This figure shows the constraints on F sigma 8 from Wallaby and 4HS separately. It implies that deviations from the expected growth index of 0.55 that are as small as 10% will be detected with about 3 sigma confidence. Of course, the strongest constraints come from combining all the new surveys, north and south, both Tully-Fisher and fundamental plane. Combining peculiar velocities from DESI in the north with Wallaby and 4HS in the south will provide about 5% precision on the growth rate in 0.05 bins of redshift out to a redshift of 0.15. Including DESI and 4HS redshift space distortions will extend such constraints out to redshift 0.4. And that will provide a really stringent test of the lambda CDM model and general relativity. Combining these surveys is also valuable because peculiar velocities are very subject to systematic errors, so having independent measurements using different methods on disjoint samples in the same volume will provide critical checks on the reliability of the derived velocity field. In summary, this increase in sample size and precision for peculiar velocity surveys is comparable to the step taken in redshift surveys by 2DF GRS and SDSS, and should have a similar impact on cosmology.